let me just make sure that this is quite clear, okay? Again, all pulsars, every pulsar that we've ever observed is always a neutron star. But not all neutron stars are pulsars, right? The pulsar effect comes from the fact that the beam of radio waves, acts like a lighthouse in that the axis of rotation and the axis of the magnetic fields are different, and so the magnetic field is essentially where the pulses are where the radiation is coming from, and so because that only sometimes points in our direction, it seems as though this pulsar is giving pulses, okay, of radio waves, but it's constantly sending out radiation. It's just that that radiation just sweeps in our direction certain times, just like a lighthouse. All right. So again, what I was saying in the last video is what we observed in the early 1990s, and this was actually from Arecibo, which is a giant radio telescope that's actually built into the side of the side of a like between two, a valley between two mountains, or between several mountains actually. It's in Puerto Rico, so it's controlled by the United States. Anyhow, in the early 1990s, they noticed that the pulses were actually varying, but they were varying in a regular manner, as it says right here. And so from that, some people thought perhaps that that this variation was due to some orbiting object, and then further studies, a few years later, concluded that indeed that there were. I think the very first one was that they first detected 2 planets, and then a little bit later they found that there was actually 3 planets orbiting this neutron star. And in fact, the very first Earth-sized planet was actually discovered orbiting a neutron star, which is kind of an ironic turn of events, because an Earth-like, we look for Earth-like planets in hopes of finding some civilization, perhaps some alien civilization, or at least some form of life. But if there was at one point some form of life on that Earth-like world, when that neutron star, before it became a neutron star, of course, it went supernova, and all life would have been wiped away from that. In fact, it probably would have destroyed any planetary system that was immediately around that star. And so, the planets that are there, in this thing that we're observing now, might have even been captured planets, or planets from like its companion. If it was in a companion, in a binary system, they might have been the planets from the binary star. Right. So anyhow, we talked about X-ray bursts, and that, of course, is we reason that has to do with the fact that these pulsars, or neutron stars, I guess I should say, are in binary systems, and matter accumulates in an accretion disk, and then the accretion disk, of course, slowly falls onto the surface of the neutron star, and then thermonuclear fusion takes place on the surface, and there's this giant X-ray flash. When hydrogen turns into helium, it's this giant explosion of 10 billion atomic bombs going off at once, and so that's an X-ray burst. And then we found ironically, I think this was in the 1970s or so. Might have been in the 80s. We put satellites in orbit, and of course there are many satellites in orbit that the military controls, and the military was looking for gamma ray bursts from the Earth. And the reason for that, of course, is that shows that there's a nuclear bomb went off. Right? If a nuclear bomb goes off, it will definitely emit gamma rays. Right? And gamma rays occur when there's a nuclear reaction, a very strong nuclear reaction. But anyhow, this satellite, which was first purposed for military use to look for we had a nuclear test ban treaty with various nations around the world, and they were trying to find violations of that. But they found these gamma ray bursts in all sorts of directions. So in fact, they reasoned very quickly that they were coming from all directions, and therefore really had to be outside of the Milky Way. Because if they were primarily in the Milky Way, there would have, let me get to the mouse here, there would have been just a section of sky where the Milky Way is, where all the stars of the Milky Way are, and it wasn't in that direction or any of those directions. It was everywhere, and so these gamma ray bursts seem to come from other galaxies, and in fact, many of them do, as we'll see. All right, so these are extremely energetic bursts of energy that in some cases take less than a second, or maybe just a matter of seconds, and these are. Remember, the human eye, of course, can only see in the visible part of the spectrum. But let's just use our imagination for a minute. If we could see in the X-ray region, and we, if one of these things occurred one particular night that you're outside, it would be as though, in the middle of the night, all of a sudden there was, like 100 suns. We only have one sun in the sky, but imagine 100 of them, or even 1,000 of them occurring. So some of these gamma ray bursts are producing that much energy. Right? So this is an example right here. This, of course, is in the gamma region, which the human eye can't see. So what we do is we artificially, make these. We use these pictures. I mean, would be gamma rays, which again the human eye can't see. So we fill it in with what we call false color to emphasize. This is an incredible amount of energy. Now look, this is something that is, this particular one that we're looking at is from an object that is 2 billion parsecs away. Remember, 2 billion, 2 times 10 to the 9th parsecs away. Right? That's a very, very distant galaxy. That's not even a nearby galaxy, right? All right. So, what in the world are these things? And so theoretically, we've figured out, what in the world could cause such an incredible outpouring of energy, and we think that it perhaps is, let's say, 2 neutron stars that are in a binary system. Both stars turn into neutron stars, and those 2 neutron stars will actually merge. And then the other one is what's called a hypernova. So it's kind of like a supernova on steroids, if you will, where you have this tremendous amount of energy pouring out into the universe, more than even a supernova. so we originally had these two models, and it turns out it's probably both. The gamma ray bursts that are observed, it's probably both of these things happening. In different occurrences. Sometimes it's going to be neutron stars merging. Sometimes it's these hypernovas, and we're still trying to figure out what exactly a hypernova is. It would be like the best description of it would be like a type 2 supernova, right? Remember, type 1 supernova, there's nothing left. But imagine a type 2 supernova where there's absolutely nothing left. Like everything turns into matter streaming out from the explosion and energy, and the stuff that's in the form of energy is in the form of gamma rays. All right, so this is just showing us, let's see, short bursts. So this is what we've reasoned out. Remember, we're still working on this. People are still debating it and trying to research it. We think the shorter bursts must come from sources that are no larger than about 300 kilometers in size, right? So that's in diameter. So that's an extremely small object, and so that must be that we think is two neutron stars that collided with each other. And the longer ones, the longer gamma ray bursts, are coming from hypernova. Remember, like a supernova takes sometimes several hundred days. So these hypernovas, which are going to be shorter in period, but they're taking more time than than can be explained by two neutron stars coming together. Okay, so, all right. Let's see. This is an example of a let's see, the difference in the blue iron and the green silicon sulfur distribution may indicate a hypernova remnant. All right, so we have up to this point we talked about anywhere from about after the supernova has occurred, right? Remember, matter is coming off of these things. So you started with an object that is 8 times the mass of the sun. So it's losing matter due to solar wind and the actual explosion of the supernova as well. And then if it's a type 2 supernova, anywhere from 1.4, right? Remember, that's the Chandrasekhar mass, to about 3 solar masses. If that remains, that's what leads to a neutron star. Okay? Because then only neutron degeneracy can hold up something that has a mass of anywhere from 1.4 times the mass of the sun to 3 times the mass of the sun. But what if the remnant after the supernova occurs is greater than 3 solar masses? Well, what happens then is the ultimate fate of a dying star. Nothing can hold it up. Basically, even neutron degeneracy pressure will not win against gravity. Gravity, if you have more than 3 solar masses, gravity will collapse that object down to a point of infinite density. And that point of infinite density is what we call the singularity, the center of the black hole. The reason it's called a black hole is because gravity is so great that even light itself, the fastest thing there is in the universe, cannot escape. All right, so, basically the escape velocity reaches the speed of light, and so that's why it's called a black hole. The region from the center of the black hole, which is also known as singularity, to the outer edge, that radius is called the Schwarzschild radius, because there was this guy in World War I who actually worked out the size of a black hole. So it actually is not as hard